Okay, let's talk about slope fields and Euler's method. So, a slope field for a differential equation, and this is a first order differential equation, so it only involves the first derivative, and the y prime is given as a function of possibly both x and y. So there's some formula involving both x and y, and that's our first derivative. And a slope field for that is, I'll show you an example, but for right now I'm going to describe it as it's a graph that shows a bunch of little line segments, and there's going to be one line segment whose slope is this function of x and y at each point xy. And I don't really mean each, like every single point. I mean many points. We'll see an example in just a second. In fact, let's see an example right now. So here are some slope fields. In fact, for our next example, we're going to be given three differential equations. Of course, y prime is the same as dy over dx. So this, they wrote dy over dx, but it's the same as what we're talking about here. And we have three possible differential equations, and we're going to match which one goes with which slope field. So these slope fields are like what I was describing a second ago, and it's not that at every single point in the entire plane we have a line segment. We just choose a lot of points. You get a better picture the more points you pick. Like this is at a scale of, like, I guess these marks are a unit distance of 1. So you get a more accurate slope field if you draw these segments closer and closer together, but you also get something that's much harder to look at. It gets very jumbled. Okay, so let's match this. And the way we match this is we look at the slopes of these line segments. I don't know if you can see. Of course, I'll scan this like normal, but we have this scaling, so this is like -1, +1 on the x-axis, and so on. And so I can pick particular points, x and y, and look at a differential equation, and this will tell me what the slope should be. And if the slope doesn't match, then I know that this one doesn't match with this one. Or if it does match, then I start to suspect that it does. And there's only three things, so we can kind of use process of elimination here. So let's pick something out, I guess. One easy thing to do is look for horizontal line segments, because that's a slope of 0. Like this one here, I see some horizontal line segments going all the way across here, which is all at a y coordinate of 2. So this leads me to believe that whatever differential equation matches with A, whenever y is equal to 2, that should give me a slope of 0. So looking at this one, if I plug in 2 for y, I don't necessarily get 0. It depends what x is, but if x isn't 0, then I'm not going to get 0 just from plugging in 2 for y. I'm going to get -x over 4. This one, if I plug in 2 for y, well, it doesn't even depend on y. So this only depends on x, so I don't see why I would get 0 if I plug in y equals 2. This one looks like the one. I get 0 if I plug in y equals 2. So I am thinking that 3 goes with A. Okay. What else can we do? So on B, I get, well, we can try the same method, because I see horizontal lines. I just noticed that I see horizontal line segments whenever x equals 0, like all up and down here. So if I look at my equations, I see number one, if I plug in x equals 0, I am going to get 0. And yeah, by the way, of course, the slope of a horizontal line is 0. That's why I'm looking at this. The differential equation is supposed to be telling me the slope, and a horizontal line has a slope of 0, so I'm looking to get 0. So these horizontal lines are when x equals 0, and sure enough, when I plug in x equals 0 here, I get 0. Because this could be sort of like a false positive, let me make sure that this one doesn't work. Because cosine of 0 is 1, so if I put in 0 for x, I'm not going to get 0 here. So it looks like 1 is b. And then that, if all we're trying to do is answer the question, that means 2 has to be c. But let me keep talking. Some of the best parts is when I keep talking despite the fact that we've completely answered the question. This is where the real conversation begins. There's a lot more things that we could notice about this. There's a lot more ways that we could answer this question. One feature that I notice is that if I look at the slope field A, the slope doesn't seem to depend on x. So what I mean by that is if I go like across a horizontal line, the slope doesn't seem to change. Like as I'm moving my pen across, all these line segments seem to have about the same slope. And if I move my pen a little bit down and go straight across, all these have the same slope. All these have the same slope. And in fact, if I go across, I just see a bunch of line segments of the same slope. So this slope doesn't seem to depend on x. And this differential equation depends on x. This differential equation depends on x. This is the only one that doesn't. So if I didn't decide already that 3 had to go with a, that would be another clue that 3 goes with a. Similarly, if I look at C, if I move my finger vertically, I see a bunch of line segments of the exact same slope. So whatever differential equation goes with C is something that doesn't depend on y, like 2. In fact, 2 is the only one where the differential equation has an x in it but not a y in it. Anyway, so those are slope fields. We'll do more examples like that. All right, so let me tell you Euler's method. So Euler's method is basically an approximation method. Differential equations are very hard, and in this class we're going to learn a couple of tricks for solving them. If you take a differential equations class later, then you will learn several more tricks, but the truth is differential equations are often, it's like integrals. They often don't even have elementary solutions. So despite the fact that we're going to learn a lot of tricks to solve them, sometimes you just have to basically give up and settle for an approximation. So we're going to get that out of the way now because this is an approximation method. So suppose we're given an initial value problem. So y prime is a function of x and y just like before. And because this is an initial value problem, we're going to be given a point that the function goes through, like y of x naught equals y naught. What we can do is we can approximate another point on the curve as long as it's nearby that we're going to call x1, y1. And so I drew a picture here. We know that our function goes through this point, x naught, y naught. And I'm going to say that x1 is somewhere nearby. So I'm going to say x1 is like x naught plus some small number h. And what I would like to do is I would like to approximate the y coordinate that goes with x1. So the idea for this is we have our differential equation. So I have a point that my curve goes through. And the differential equation tells me the slope of the curve at this point. So I'll draw something. So it's like we know that my curve, whatever it is, it goes through this point and it has a certain slope. So if I want to approximate this nearby point, one idea is I can just act like my curve is a straight line. It probably isn't, but just for an approximation, we can pretend that it is. It's just a straight line whose slope is whatever this is. We can call that y1. And so if that's the idea for an approximation, what are we going to do? Well, the slope, rise over run, so it's the change in y over the change in x. In other words, it's y1 minus y naught over x1 minus x naught. Well, that's the slope, so it should be approximately this, because this is my y prime. In other words, that's the slope. So I set this approximately equal to this, and of course x1 minus x naught is just h, so that's h. And then we're trying to figure out y1, so I just solve for y1. So I multiply the h over and I move the y naught over, and y1 is approximately this. And the cool thing about Euler's method is that we do it again and again. Once I know my new point, x1, y1, I can use that. Like I started with x naught, y naught. Now I have an x1, y1. I can use this same formula to get an x2, y2, and then use the same formula again to get an x3, y3. So to help us use this again and again, let me write it in this form. The new value of y is just the old value of y plus h times the old slope. In other words, f of the old values. This is the same as this, except y1 I'm calling y new, and sub-zero means old. So let's do a concrete example of this. We're given a particular differential equation, and it's an initial value problem, so I have this information. So my x naught, y naught is the given point, where x is 1, y is 2, and we're going to find x sub 2, y sub 2. So let's make a little chart. This is probably not strictly necessary, but let's do it. So x0, y0, that's given. Now we use the formula. So actually, maybe as I was writing this, I should have also written, this is much easier, but the new value of x is always just the old value of x plus h, right? That's what we did. x1 was x naught plus h, so to get the x values, I just keep adding h. So this is going to be easy. I need to go up to n equals 2 because I need x2, y2, and I just keep adding h, and h is 0.1, so it's going to be 1.1, 1.2. Okay, so let's fill in the y values. Well, I'm using this formula. So y1 is going to be y0 plus h times f of x0, y0. In other words, that's 2 plus 0.1 times, okay, I'm plugging in x0, y0, which is 1 and 2, into this. Oh, you know what? Okay, this will be a little bit of a funny example because this is 0. So this just gives me 2 again. So actually, this did not change. Okay, I'm going to go through with this. It is what it is. We'll definitely do another example later where things are a little bit more interesting, but let me just finish this. I just need to fill out y2. And what I'm noticing is, so let me tell you what we're going to get. We're just going to get 2 over and over again, because what I keep doing is I keep taking the old y value, and the old y value is still 2, and then I go plus h is 0.1. Oh, no, wait. I was wrong. I'm sorry. It's not going to be 2 over and over again. That's good, because I didn't want this to be boring. Yeah, forget I said anything. Let me just pretend that well, let's just keep going. Yes. What am I doing? This is the old y value plus h, and what I'm about to do is f of x naught, y naught. So f is this function, so it's 2 times x sub old, so I take my previous value of x, which was 1.1, and then I subtract y, which is 2, and then this is 2 plus 0.1 times, okay, this is 2.2 minus 2, so that's 0.2. So 2.02. So I was wrong. It wasn't 2 over and over again. It's not that far off, but okay, good. So my x2, y2 is that. Great. Of course, these approximation methods, it's good to know in theory how they work, but of course a computer can churn this out way faster than us. If you choose a smaller and smaller value of h, the approximation gets better and better, and so a computer can use a tiny value of h and it can churn out a table that's really long like this in a matter of seconds. So this isn't a practical thing in the year 2025 for us to be doing by hand. We're doing it by hand so we understand how it works. That's the only reason. And computers use this and some more sophisticated approximation methods to approximate solutions to differential equations. Anyway, so as I promised, we are going to learn some tricks for actually solving these. Like exactly, not approximately. And so this is the very first trick we're going to learn for differential equations that we call separable. So a differential equation, and I just wrote the same thing I've written several times, y prime equals f of xy. Of course, y prime is the same as dy over dx, and sometimes we prefer to write it this way, but this is the same. We say it's separable if we can sort of algebraically rearrange it and possibly, typically this involves moving things to either side. So we rearrange it using algebra to be separated. This is why it's called separable. And the important thing here is that all the y's are on the left along with the dy, and all the x's are on the right along with the dx. So you can get it in this form. And if it's possible to get it in that form, which it isn't always, if it is, we call it separable, and in that case, we can just integrate both sides. So let me just show you through an example. So we're going to solve this initial value problem. So here we go. First, I'm going to write dy over dx. For separable differential equations, you always want to write dy over dx instead of y prime, because ultimately I'm going to have the dy on one side and the dx on the other side. In fact, let me just cross multiply, because I get y dy equals negative x dx. And just like that, all my y's are on one side with the dy, all my x's are on the other side with the dx. So what we do from here is we integrate both sides. So this is an integral with respect to y, and this is easy to do. This is 1/2 y squared, and this is negative 1/2 x squared. And typically when we integrate, we write plus c. There's no reason for me to write, like, I'm not going to write plus c on this side and plus c on the other side. First of all, they would have to be possibly different constants. So maybe there's like a c1 here and a c2 here. But even if I wrote that, I could move all my constants to one side and just have a single constant. So in this step, I just write plus c on one side, and it doesn't matter which side it is. Okay. For an initial value problem, we should be able to figure out c. So this is telling me that when x is 3, y should be 4. So when y is 4, this is 16. So 8 equals negative 9/2 plus c. So c is 16/2 plus 9/2, that's 25/2. We could leave our answer like this. This is what I would call an implicit solution. Implicit because it's not solved for y. I am usually okay with implicit solutions, but sometimes I and many times other people would want an explicit solution. So it's not hard. We would just solve for y. First of all, let me just multiply everything by 2. So I get this. And so y is plus or minus square root of that. And we should be able to figure out whether we really mean a plus or a minus. If we go back to the initial value problem, or the initial condition, that's what this information is called. If I put in 3 for x, I'm supposed to get 4 for y. In particular, I'm supposed to get a positive number, so it better be the plus. So this would be an explicit solution. The value of this is, first of all, this is an actual function. If you look at this original equation, like if I get the x squared and y squared on the same side and I multiply by 2, This is actually just x squared plus y squared equals 25, which is a circle, of course. This is a circle of radius 5. Which is not actually a function, because it doesn't pass the vertical line test. This is two functions. The top half of the circle is one function, the bottom half is another function, roughly speaking. And we sort of lose that information if we're just giving an implicit solution. Usually I'm okay with implicit solutions, but this is the disadvantage, is it doesn't actually give you a single function. The explicit solution gives me a specific function. By the way, when we solve for y and there was this plus or minus, deciding whether that's a plus or a minus is just deciding whether we're talking about the top half of the circle or the bottom half of the circle. As it turns out, we were talking about the top half, and that's what this is.